Yeah, so I know it's been a long, interesting day, so I'll try and keep this on the short and sweet side, but I will give you an overview of the project before I focus in on my work on the 29 to 46 region, and it has really, really been a great honour to be Ian's final PhD student. And it started off relatively normally, some very lovely dinners with very lovely company, and then it got a little odd because, of course, I was doing my PhD, as a few others were, during COVID. And this is where I was when Ian realised, and much to his annoyance, he still doesn't like that I don't check my emails often enough, because he contacted me via Instagram to tell me I should rather have a look at my emails. But when they did let me back in the lab, we worked ferociously to see how much more of this project we could get done. Now, I'm going to take us back to basics. One of my favourite facts about natural products is that 26% of pharmaceuticals are based on natural products or derivatives. And as many of us already know, the marine world is a less explored source of these natural products. And what we see in many of these natural products is interesting bioactivity and often novel mechanisms of action. But the complexity that we see in these molecules is rather a double-edged sword, because while it means that they can have these potent effects and novel mechanisms of action that we're interested in, it also means that they're very difficult to synthesize. And we're going to need to synthesize them often to find out more about that mechanism, often to fully characterize the molecule, and then let alone any further biological or clinical studies that we might want to do. So our molecule of interest, hemicalide, was first published in the patent literature in 2011, and it was obtained from a hemicalide sponge collected in the South Pacific Ocean. Bioactivity guided isolation on 5 kilograms of the sponge gave only 0.5 milligram of hemicalide. Fortunately, this was enough for preliminary characterization, bioactivity, and mechanistic studies. And I think our avid interest in hemicalide stems largely from its nanomolar and sub-nanomolar level cytotoxicities against numerous cancer cell lines. Mechanistic studies also indicated that there was a novel mechanism of action, and unlike a lot of other cellular cytoskeletal disruptors, this appeared to happen at not one but 2 stages of the cell cycle. So high-res spec determined the molecular formula of hemicalide, while extensive 1- and 2-dimensional NMR studies permitted the assignment of the planar 46 carbon skeleton. There are 21 stereocenters, so that gives rise to over 2 million possible stereoisomers. And due to the small amount of hemicalide isolated, the absolute stereochemistry is not known for any of these stereocenters. Over the years, what we've referred to as the stereo conundrum of hemicalide has begun to be solved through careful work using 2D NMR, computational, and synthetic studies. The Cozy and Artisan groups have also contributed to synthetic efforts towards hemicalide. Now, within the Paterson group retrosynthetic analysis, we broke the molecule, as usual, into smaller stereo clusters, with the first major disconnection involving a boron aldol reduction and O-methylation at the C28-29 bond to break it roughly in half. My work is that shown in green. So the C21 to 28 region is disconnected by a Stille coupling to reveal the dihydroxylactone and polypropionate stereoclusters. Disconnection of the C29 to 46 region by cross-metathesis reveals the alpha-hydroxylactone and C29 to 35 stereoclusters. 3 colleagues before me constructed the polypropionate and dihydroxylactone stereoclusters, and I'll just touch briefly on that. So synthesis of the dihydroxylactone stereocluster bearing an 18-19 syn relationship at the box at the top showed that this was a much closer match for hemicalide than the 1819 anti-diastereomer previously synthesized by the Cozy and Artisan groups. Furthermore, coupling of the dihydroxylactone to both enantiomers of the polypropionate region revealed that the 1318 syn acid was a better match for hemicalide than the 1318 anti-acid previously proposed by the Cozy and Artisan groups. So through these efforts, the relative stereochemistry of the C1 to 25 portion of hemicalide has been quite convincingly established. Now, the exploratory synthesis by the Cozy and Artisan groups of multiple diastereomers of the hydroxylactone stereocluster established the relative stereochemistry within the C36 to 42 region. This was supported by our own computational analysis, leaving only 5 unassigned stereocenters. We still wanted to solve C45 right at the end, which, although not distinguishable in Cozy and Artisan's work, was indicated to be distinct by our own computational analysis. And I think this is one of Ian's charms. If something appears challenging, if someone else hasn't been able to do it, he's still going to give it a go. And I really appreciate him pushing me at the times that it was hard to do that. In contrast to the flexibility needed when synthesizing numerous diastereomers, we aimed for a more efficient and highly asymmetric synthesis of the region. And for this synthesis, I just wanted to highlight a few key reactions. So firstly, I think one of the reactions that I'm most proud of in my PhD was this early asymmetric IPC boron aldol, which is rather fitting. It proceeded, after some adjustments, relatively smoothly to allow creation of the first region of the fragment backbone. Not only did my hard work and optimization eventually pay off, but when I managed to get a 91% yield, Ian laughingly called me the queen of the aldols, and I think that was when I felt like I had a place in the group. Although, as Gordon pointed out in my Viva last week, it is a little odd that we really did need the IPC ligands to go from 2 to 1 DR to the over 20 to 1 DR that we really wanted going forward. Next, it was more challenging than we initially expected to create the lactone with the correct hydrogen orientation at C38, so in the small red box on the right. The first pathway we tried was reduction of the unsaturated lactone, or cyclic enowate. It was necessary to really push this reduction, and even on gram scale, only the undesired product was detected. Perhaps this makes sense when you realize that the trans-diaxial attack on the unsaturated lactone proceeds preferably through a chair-like transition state to give a product where both of the large chains are placed equatorially. In contrast, in the desired product, unfavorably, one large substituent would be axial, or you would have to occupy a twist boat form to avoid that outcome. So the next approach was to try reduction on an acyclic enowate. Even then, multiple reactions were tried before the one shown here, and it is a Crabtree catalyzed hydroxyl-directed hydrogenation that turns out to proceed much better when run at -20 for a week, a fact which serendipitously I discovered when the heating broke in the chemistry department over winter. Lastly, to asymmetrically reduce C45 proved a challenge, with none of the typical methods achieving satisfactory results. In the end, a dive into the literature turned up some great 1980s chemistry and the revival, at least in our lab, of the Terashima reduction. This uses a partially decomposed lithal. So although the reaction mechanism hasn't been established, it was proposed that the steric interactions of the substituents of the enone with the methyl and phenyl groups of the N-methylephedrine and ethylaniline, and the electronic interaction of the carbonyl oxygen with the lithium cation controlled the face from which the reducing agent approached the enone. So the resulting hydroxyl orientation was confirmed by Moshe's, and also it matched small samples that we were able to get through CBS reductions, which didn't scale up well. But it allowed us to continue. Thankfully, after producing both of the C45 diastereomers, deprotecting the complete fragments, running proton and carbon analysis on a 700 megahertz spectrometer and comparing the results with the natural product, I was able to show that the 4245 diastereomer was a closer match for the natural product than the 4245 syn diastereomer. So that's one of the two remaining fragments. This left only 4 unassigned stereocenters in the C27 to 32 region and the relationship between the stereoclusters to be determined. During my work on the hydroxylactone region, the Cozy and Artisan groups jointly published a carbon backbone stereoisomer. This molecule bore a 13-18 anti-relationship, contrary to that which we showed to be a better match for the natural product data. And the remaining 5 unassigned stereocenters, at that time including C45, had been arbitrarily assigned and showed significant deviations from the natural product. The molecule was also unable to be fully deprotected, and some uncertainty was expressed as to where that remaining protecting group was attached. Fortunately, some very helpful information can be gathered from the backbone stereoisomer. Analysis of the NMR data, as I said, shows significant deviations from the natural product, which indicates that the C27 to 32 region, as shown, does not match that of the natural product, but also suggests that the opposite relationships, so namely 31-32 syn and 27-29 anti, are more likely. So practically, this allows our synthetic targets to be narrowed down from a total possible 16 to 5. So we'd want both enantiomers of the syn-anti-anti arrangement on the left, both enantiomers of the syn-syn-anti arrangement in the middle, and then one of the C27-29 syn arrangements to double check that relationship. However, if the C32 to 36 relationship between the stereoclusters could be established, only 3 of the 5 C27 to C32 options would need to be made. To this end, a streamlined route to access enantiomers of the C29 to 35 region was developed. Brown protoboration with cis-butene gives the syn stereocenters, with the enantiomer selectivity being controlled by the choice of chiral IPC boron component chosen. Hydration gives us the primary alcohol, which can be extended to the desired chain length by an oxidation-Wittig methylation sequence. With our 2 terminal olefins in hand, we pursued a metathesis cross-coupling strategy. So cross-metathesis thermodynamically favours our desired E geometry, delivering the C29 to 46 olefin. At this stage, the desired olefin is inseparable from the small olefin dimer. In fact, at first I thought that the reaction had failed due to the excess of the small olefin dimer, because by NMR you actually can't see your desired product at all. And it was only with a little mass spec that we were able to see that it was indeed there. So PMB serves to give us a nice polarity difference. We have an alcohol and a diol, and we can separate for the global deprotection, which gives us our tetraols to compare to the natural product. A lot of data summarized into one slide. Analysis of the mean sum of errors and maximum errors of these diastereomers strongly indicates that the syn-anti-anti configuration best matches that of hemicalide. Oxidation of the syn-anti-anti C29 alcohol gives the C29 to 46 aldehyde ready for coupling with the remainder of the molecule. This leaves us 1 carbon-carbon bond and 5 steps away from the 8 possible hemicalide diastereomers. So we've gone from over 2 million stereoisomers down to 128 before I stepped into the lab, down to 8. We're 1 carbon-carbon bond away to be formed, I think rather fittingly, by an IPC boron-mediated aldol. And we have 2 outstanding stereocenters and the relationship between the stereoclusters to be determined. And I think that really does show the power that total synthesis still has, especially when in instances where we may not be able to characterize the molecule in any other way. So, Ian, it's been an absolute honor. I think I've been able to monopolize your time more because I've been the last one. And yeah, thank you.